As Princeton scientists examine tiny fragments of a meteorite that landed on Earth some 15,000 years ago, they find something astonishing. To begin with, the experts discover that pieces of the rock are composed of an incredibly rare mineral called khatyrkite, which in itself is rather remarkable. But as it happens, that's not the only surprise in store. You see, the khatyrkite contains a crystalline structure that seems to defy the laws of earthly physics. In fact, it looks rather alien. Scientists unearthed a meteorite in Siberia, and inside they made an extraterrestrial discovery. And while researchers had twice uncovered similar crystalline materials in the khatyrkite meteorite, this new discovery isn't identical to those earlier finds. All three clusters are different, although it appears that each of these so-called quasi-crystals have a common property. Amazingly, nothing like the three quasi-crystals from the khatyrkite meteorite exist naturally anywhere else on Earth. And this raises an intriguing question. If these structures are so rare, are they actually from our planet at all? Could we instead be dealing with something that's normally only found in outer space? Well, one of the scientists best equipped to answer this question is Princeton University's Albert Einstein Professor in Science Paul Steinhardt, who has been closely involved in the study of the quasi-crystals in the khatyrkite meteorite. And in order to determine exactly what the rock contained, Steinhardt had to turn detective. Back in 2009, the only known sample of khatyrkite was held in the Florence Museum of Natural History in Italy. When Steinhardt and his colleague Luca Bindi sent this sample to Princeton geologist Lincoln Hollister, though, there was initial disappointment. At first, Hollister believed that the quasi-crystal must have been a byproduct of an industrial process on Earth, rather than something that had arrived from outer space. But after further study, Hollister, Bindi and Steinhardt eventually came to the conclusion that the structure couldn't have been man-made. And this was thanks in part to one material in the meteorite: stishovite. Of this version of silicon dioxide, which itself is exceedingly rare, Hollister declared, "This is not something that is made in an aluminum smelter on the surface of the Earth." So, Steinhardt realized that this quasi-crystal hadn't been created by humans, instead, it had formed naturally. And this was a startling finding. After all, scientists had previously believed that quasi-crystals, which had been purposely made in labs as far back as 1987, were too unstable to actually occur in nature. Now, though, just one question remained. Had the quasi-crystal been formed on Earth or elsewhere? Before we get onto the answer to that puzzle, however, let's learn a little more about these mysterious quasi-crystals. The story starts with Daniel Shechtman, who in the early 1980s was employed at Maryland's U.S. National Institute of Standards and Technology. And in the course of his work, the Israeli scientist made a surprising discovery. Studying a manganese and aluminum alloy, Shechtman came across a crystalline pattern that he'd never seen before. The normal format of crystal structures is one of repeated symmetrical patterns such as triangular or cuboid shapes, for example. But what Shechtman saw was a cluster within which each shape was different. This was a quasi-crystal. Pat Thiel, a materials scientist at Iowa State University, gave the practical example of laying tiles in order to illustrate the properties of quasi-crystals. Speaking to PBS in 2011, the professor explained, "If you want to cover your bathroom floor, your tiles can be rectangles or triangles or squares or hexagons. Any other simple shape won't work because it will leave a gap," Thiel continued. In a quasi-crystal, imagine atoms are at the points of the objects you're using. What Danny Shechtman discovered is that pentagonal symmetry works. But while triangles or squares fit together snugly, the pentagon-shaped quasi-crystals leave spaces in their pattern. These voids are then filled by what Thiel refers to as glue atoms. Yet some scientists ridiculed Shechtman's quasi-crystal findings for years, as they simply couldn't believe that the accepted wisdom about crystal structures could be completely overturned. In fact, the director of the National Institute in Gaithersburg even asked Shechtman to vacate his position. In a 2011 press release from Iowa State University, Shechtman recalled, "For a long time, it was me against the world. I was a subject of ridicule and lectures about the basics of crystallography. The leader of the opposition to my findings was the two-time Nobel laureate Linus Pauling, the idol of the American Chemical Society and one of the most famous scientists in the world. A 2011 Reuters article even quoted Pauling as saying, "There is no such thing as quasi-crystals, only quasi-scientists." And in the Iowa State release, Schechtman explained of his fellow scientists' stance: "For years, till Pauling's last day, he fought against quasi-periodicity in crystals. He was wrong, and after a while, I enjoyed every moment of this scientific battle, knowing that he was wrong." But the well-deserved reward for being right about quasi-crystals was the Nobel Prize in Chemistry, which Schechtman received in 2011. And if you think that the notion of quasi-crystals being formed in labs seems far removed from everyday life, think again. In fact, examples of these structures may even be in your home right now. Because quasi-crystals hamper the conduction of heat, they're ideal for both non-stick pans and LED lights, as well as surgical apparatus. And Professor Bassem Shakashiri of the University of Wisconsin-Madison told PBS that quasi-crystals' potential as a material will only be further realized in the future. Yet Thales' early groundbreaking work on quasi-crystals had been concerned with man-made samples. It was largely believed, too, that quasi-crystals were simply too volatile for natural formation. This theory was challenged, though, by Steinhardt and Bindi's analysis of the khatyrkite that they'd found in Florence's Natural History Museum. Steinhardt had actually been looking for evidence of naturally formed quasi-crystals from 1999, but it was only 10 years later that he came across the Florence sample of khatyrkite. Then, once it was established that the Italian specimen did indeed contain naturally formed quasi-crystals, Steinhardt felt the need to investigate further. Steinhardt subsequently dispatched a fragment of the Florence khatyrkite to the California Institute of Technology. There, scientists discovered that the sample contained oxygen isotopes, which showed that it must be from a meteorite. In other words, the quasi-crystals had been naturally created but not on Earth. And it appeared that the formation had happened over 4 billion years ago, so, at around the time when our sun was coming into being. Now that Steinhardt could be certain of the extraterrestrial origin of his quasi-crystals, he realized that he needed to find more of this material. But where had the Florence Museum sample of khatyrkite come from? Speaking to Quantum magazine in 2014, Steinhardt said, "We had to discover how the rock managed to get to the museum. All we had was a box." And that brings us back to why Steinhardt had to turn detective. In short, he had to track down the origin of the khatyrkite. To begin with, the theoretical physicist seemed to have a promising lead, too, as while rooting around the Florence Natural History Museum's records, he managed to find a letter. This message claimed that the box containing the khatyrkite sample had come from Amsterdam in the Netherlands and that a collector in the city called Nicholas Kokek had sold it to the museum. But, frustratingly, no trace of this particular Kokek, a typical name in Holland, could be found. Then came an unbelievable stroke of luck. While Steinhardt's fellow researcher Bindi was at a dinner party in Florence, he entertained the other guests with the tale of the mysterious khatyrka meteorite sample and the elusive Kokek. And, incredibly, one of the diners spoke up to say that she knew an elderly woman called Kokek who resided on the same Amsterdam street as her. When that dinner guest arrived back in Amsterdam, moreover, she asked her neighbor Mrs. Kokek if she knew a collector with the same surname. And it turned out that she did indeed. The man in question, Nicholas Kokek, was her late husband. This news was enough to get Bindi straight onto a flight from Florence to Amsterdam. Furthermore, although Mrs. Kokek had no knowledge of the boxed khatyrkite fragment, she allowed Bindi access to her late husband's papers. And an entry in what Mrs. Kokek called her spouse's secret diary revealed something intriguing. Apparently, the collector had bought the sample from someone called Tim in Romania. But while this information initially looked promising, it was ultimately a dead end. Talking to Quantum magazine, Steinhardt recalled, "We spent 6 weeks trying to find Tim and didn't get even a smidgen of a hint. I sent Luca back to this woman to see if she knew anything about Tim the Romanian. She didn't. But she revealed that her husband used to keep a secret diary. And this item was to prove more informative. The secret diary showed that Kokek had in truth bought the sample of khatyrkite from one Leonard Razin at Russia's Institute of Platinum in St. Petersburg. Bindi had heard of Razin, too, as the man had announced the first find of khatyrkite back in the 1980s. Then the khatyrkite had been acquired by Kokek, who in turn had subsequently sold it on to the Florence Museum. Another example of the mineral, meanwhile, was at a St. Petersburg attraction. So, Steinhardt subsequently sought out Razin in a bid for further information. Unfortunately, though, Razin couldn't give a precise location for the find. All that was known was that the sample had been discovered in the Koryak Mountains. And as the Koryaks are the second largest mountain range in Siberia, that didn't narrow things down much. It seemed, then, as though Steinhardt and Bindi were back to square one. But, apparently wishing to press on, Steinhardt decided to reread Razin's 1985 report about the khatyrkite. This looked to yield a promising lead, too, as it referred to a certain Valery Kryachko who'd been involved in the finding. And a breakthrough duly came. While browsing a Russian scientific publication, Steinhardt saw that Kryachko had co-written a 1995 study. Steinhardt was later to recall the moment when he found Kryachko's name. "Suddenly, we went from nothing to maybe this is our guy," he explained. The physicist was then able to track down Kryachko, now in his 60s, in the Russian capital of Moscow. And with the language barrier broken down via Google Translate, Kryachko was happy to tell what he knew. It turned out that when Kryachko had been a graduate student, Razin had employed him to search for platinum. In the late 1970s, Kryachko had therefore traveled by helicopter to a Siberian location so remote that the nearest settlement was hundreds of miles away. More specifically, the vehicle had landed by a stream called Listvenitavyi. The Listvenitavyi stream is located in a region called Berengovsky in the Koryak Mountains of eastern Siberia, which in itself is an isolated part of the country. And once there, Kryachko had worked the heavy clay in his hunt for platinum. Yet while there was no sign of the precious metal, the student did come across some strange metallic lumps. Back in civilization, Kryachko then handed the curious substance to Razin. And, in fact, that was the last he had known of the matter until Steinhardt and Bindi had contacted him all those years later. But there was also some good news. Kryachko could pinpoint the exact place where he'd found the khatyrkite. This part of Siberia was so far east, as it turned out, that as Hollister joked to Quanta magazine, you can see Sarah Palin from there. What's more, this section of the country thaws for only a few weeks of the year, meaning the window for exploration was narrow indeed. Steinhardt recalled, if you had asked most geologists, everyone would agree the chances of finding anything going back was tiny, and it was probably a wild goose chase. On the other hand, the only way you had a chance was to go with Valery Kryachko. So that's exactly what they did. In 2011, a 13-strong group which featured Steinhardt, Bindi and, crucially, Kryachko himself, made their way to the far-flung spot during the brief summer thaw period. In order to get there, the team drove across the tundra in 2 snowcats from a mining settlement named Anadyr. And all in all, it took the researchers 4 trying days of traveling in tough conditions to reach the Listvenitavyi stream. Then, once at the location, the team assembled a temporary lab to analyze samples and began digging into the clay, which had an unusual blue-green tinge. The stream itself, meanwhile, was nothing more than a puny flow of icy cold water. And during the excavation process, someone stood guard with a machine gun to defend the crew from the very real threat of bears. Fortunately, it looked as though the diggers were in luck. On the first day of the process, in fact, Bindi spotted a piece of rock among the clay that he was optimistic was a fragment of meteorite. Nevertheless, the scientists worked their way through 1.5 tons of clay, which yielded a few pounds of likely samples for more than a week. Then it was time to go home. The next day we're driving out over the mountains, and we look back, and it's all white, Steinhardt later said of their departure. We got out literally the day before winter hit. Once the scientists were back in the US, however, it was down to Hollister and others at Princeton to analyze the samples. And the results of that investigation may have cheered the researchers. You see, they had managed to bring back at least 9 grains of material that would subsequently be identified as meteorite fragments. And, crucially, these pieces of meteorite not only contained seldom-seen alloys of copper and aluminum, but they also included naturally occurring quasi-crystals. Hollister and the others now spent a further 2 years analyzing the mix of matter in the khatyrkite and working out a theory as to how it had been created. The researchers believe it's likely that the mixture of quasi-crystals and other materials was initially created by a massive collision between two asteroids. In addition, the rare matter found in the khatyrkite is thought to have been originally formed by some unknown processes in the solar nebula, the cloud of space dust and debris that formed our sun, and ultimately the planets we know. Another possibility is that the more unusual constituents of the meteorite, including the quasi-crystals, could have been created by the force of asteroids coming together in a violent manner. But the scientists are happy to admit that they still have much to learn about how natural quasi-crystals have formed. As Steinhardt told Vice in 2016, it is very, very early times for these kinds of studies. Thanks for watching, and don't forget to like and subscribe.